Alrighty, so
You got plugs?
yeah, so this is not going to be a very serious talk.
Oh.
If you use any of the stuff I'm going to show you in production, I either A, want to know what company you work for, or B, never want to work for that company. And Alan, if you ask security-related questions, I'm not sure what I'm going to do.
That's your job. Yeah, that's true. I don't do that.
All right, so what we're going to talk about is untyped lambda calculus. This is like the purest of the pure in functional programming. This is actually what the core of Haskell kind of works on. There are other ways to implement very pure functional programming languages and other models that you can use, but this is one of the most common ones. And I don't have slides because it's a lot easier if we just walk through the code and we ask questions if you don't know what's going on, because things are probably going to get confusing. So let's all practice. If you have a question, you're going to raise your hand.
What's going on?
Thank you. You can also say, what the hell is this? I don't understand anything that's going on, or my eyes are bleeding. All those are perfectly valid.
What is that fuzzy creature?
How does the Y Combinator work?
That would be a different talk. How many of you here are familiar with JavaScript arrow functions? All right, so we're just going to quickly go through this for those of you who aren't. In this case, it is actually easier to write out these examples in JavaScript because it's a language you all can run in your browser if you want to play around with this. It isn't as foreign looking as Haskell, but it's relatively compact and concise for this style of programming. So if we want to write a unary function, a function that takes in one argument, we're setting a constant here to be a unary function. Here we have the first parameter, which is called param, and then we have an arrow. The arrow here says that we're creating an anonymous function, and we're only ever going to create anonymous functions that take one parameter. So we're just got parameter, arrow, and then what the function returns. In this case, the function returns calling some function called do something, passing in the parameter. Calling functions is done with parentheses like it is in most languages. To do a binary function, we have to curry the function, because in this case, we are not going to be using functions that take more than one argument. It's always going to take one argument. So how do we do a function that would take in two arguments? We create a function which takes in a parameter, which here we call param1, and it returns another function which takes in a parameter, which we're going to call param2. And in this case, that function, if you call it, will then call some function called do something, passing in param1, and then param2. In this case, do something is also a binary function, but instead of calling it with two arguments like this with a comma, instead we first call it with the first parameter, which returns another anonymous function, and then we pass in the second parameter, and then that will return the result to do that. Does that make sense for everyone?
Isn't that like defeating the point of not allowing binary functions?
So no, so this allows us to write binary functions using unary functions. Because you will want, if you want to add together two numbers, you're going to have to take in two numbers at some point somewhere. But this allows us to only ever write functions that take in one argument. All right, so often you'll see functions in functional programming languages called lambdas. A lambda is an anonymous function, which means it isn't named. It's not a closure, so it doesn't take on the scope of whatever's around it. Instead, it only deals with what's passed into it. So if you set some variable x outside the context, you can't reference x inside of some function that's in that context unless you explicitly pass it in. So that's the difference between a closure and a lambda, both of which are anonymous functions, which is another name for lambdas. If you're curious, they're called lambdas because Alonzo Church, who created the lambda calculus, which is what we're looking at in the 1930s, someone sent him a postcard to ask, why did you choose the Greek letter lambda? And he just sent the postcard back to the person and in the margin wrote, eeny, meeny, miny, mo. Just pick a random letter. It's a good letter, works well enough. It's easy to write. All right, so in here we're assigning a bunch of constants, but in really, really pure untyped lambda calculus, we don't have assignment. Everything should be able to be expressed as one function. This is just a convenience. So let's say that we have some inner function which takes in a value and then calls some other function called do something. In this case, we're not passing in the do something function. That's just a cheat to make this example a little easier. And then we are calling do something with the value that was passed in. If we nest that function, do you have a question?
Yeah, I think about that idea of we don't have assignments in untyped capital.
Mhm.
I'd like to have this. Can you expand on that a little bit?
So that's what I'm going to show you right now. So right now we have this function called inner function for assigning to a variable called inner function.
Right.
And then here we have a variable called outer function, or constant outer function. And inside of it, we're calling inner function, that named function that we created before, with whatever comes in. So in this case, we've used an assignment, but because the lambda doesn't actually rely on scope in any way, we can inline this function directly. So if we look here, outer func is using inner func, we can just take the actual code for inner func and just replace it manually like that. Now if we look at this, this can be simplified because we're creating this function and then we're immediately calling it with some value, in this case, the one called another value. So we can take this code and actually copy this thing that we're passing in, and wherever we see value in this function, we can just replace it with that. And now we've effectively called the function by inlining it. Does that make sense? So this is what's called beta reduction. So you can think of when you're evaluating lambda calculus, it's kind of like doing these sets of macros. You take a bunch of functions, you put them together, you go through this beta reduction process, and that's effectively performing your computation, and how that can do a computation, that's what we're going to look at. But that's really all there is to it, is this kind of macro replacement. We're programmers, we like to think of them as like little boxes that you put data into and stuff comes out of. That model is also perfectly fine, but this is just another way to look at it. And this will become important because, again, everything that we're doing here, whenever we assign something to a constant, we always want to have the ability to just replace and inline that. And that's going to trip us up at one point, so we'll keep that in mind. All right.
Okay, all I'm going to do is create inner function and outer function, so that's the same thing, except used a different value. But I don't get a difference between your inner function and outer function, except for the fact that they have a different input.
So imagine they did different things.
Okay.
So imagine inner
Okay,
function like incremented the value and then called it with something.
So that do something that you put in there was actually doing something else.
Yeah, so this do something, it does something else
Does
somewhere
something
else.
else.
And so now we've effectively inlined it.
Oh.
The whole reason to do these assignments of constants is just to keep us sane. If we just looked at everything as pure functions that just took variables like x and y and passed them into each other, it would look like garbage very, very quickly. And I can show you what that looks like later. But we'll give everything names because we're humans and we like to work with things that have names. It's just a convenience for us. All right, so here are the rules of untyped lambda calculus. You can create lambdas, these anonymous functions, which take one input, they don't deal with local context in any way, and then they can return one of the things that you gave it, or it can call one of the things that you gave it with something else that it has access to. So what's the simplest one of these that we can do? That would be what's frequently called null. Null is just an anonymous function that takes in x and returns x. We have to take in something and we have to return something. So the easiest thing we can do is just do the identity function. We'll call that null because that's the simplest thing that we can create. It doesn't do anything to the input. It just straight passes it through. Now, despite the fact that all we can do is take an input and call things, this is Turing complete. We can do every single computation that is computable using all of this. You could implement WordPress only using anonymous functions, past other anonymous functions, past other anonymous functions. You can do numbers, mathematics, you can implement OS X or Linux, anything is possible. It's completely Turing complete. So what we're going to go through is how you can kind of start to build up each of these data primitives. Do you have a question?
Yeah, I was going to say, it's Turing complete, but how are you going to branch that?
We will show you.
Okay.
To do branching, we'll need Booleans, right? Good segue. All right. So a Boolean function. Let's think about, remember, we don't have values. We only have functions. So whenever we have a value like a Boolean, true or false, we have to think of it as what action is that equivalent to. So a Boolean function, or a Boolean value, if we don't do anything with it, it doesn't have any point. So what do we do with it? We usually call if statements with them. We say, given two things, I either want one of them or another one. So a Boolean function can be implemented very simply. A true function is simply something that takes some value to be returned when it's true, and some value to be returned when it's false, and it just returns the one that when it's true. So we've given it two things, and it's picked one of them. False is going to be very similar, except it returns when false. Does that make sense? So here we have Booleans, we have true and false. We can go ahead and pick between two things only using functions. So how do we do operators on those? The not operator is very simple. It's a unary function. It takes in a Boolean, and it gives false to the first value and true to the second value. So if the Boolean function that you gave it is the true function, it will return the false function if you got it. And if it's the false function, it will return the true function. So we just not it. Does that make sense?
Can you explain your syntax on 28?
28 here.
Yeah.
So this is a function that returns another function, and then that returns this value. So this is, if you were writing more traditional code, you would write something like function true takes in when true, when false, and then returns when true. Does that make sense? So these two are the exact same thing. Just this is a lot more compact syntax, and we're gonna need compact syntax. All right, so next we have, and, yep.
Why didn't you use an anonymous function going to went through instead of directly went through? You say that everything should be a lambda with one argument, right?
Mm-hmm. So this is a lambda with one argument that returns another lambda with one argument.
Exactly, but you didn't make that explicit. There's a reason, or?
So that is explicit here. So in JavaScript, if you wanted to do a function that takes two arguments, you do that.
Yeah, okay.
Because this isn't like Haskell or
Scala,
where everything is automatically curried.
So
and it doesn't actually.
I wish it was like that in Scala. Unfortunately,
Okay.
it's not.
That's
Yeah.
That's not very.
No, you need to explicitly curry, but yeah.
Yeah. All right. So the and function is the binary one. So what we're going to do is we're going to take in two Boolean values, and then we want to do something similar to not. Depending on what values each of them has, we'll either return a true or return a false. So in the case of and, we're going to take an A and B, and let's look at this piece by piece. We'll ignore this bit here. If A is false is passed in, we're going to return false, because if you do an and operation and one of them is false, you return false. What if A is true? Well, now we're going to look at B. If B is also true, we return true. If it's false, it means A is true, but B is false, and so we return false. Make sense? Or is very similar. We simply switch the position where if A is true, we return true. If A is false, we only return true if B is also true. Exclusive OR is similar. We just copy and paste that little bit for B in both sides. And if A and B are true, we do false. But if either one of them is true, you return true. Now exclusive OR. So now we have all these lovely binary functions. Now, what's the simplest thing that we can do with binary functions usually is to do an if statement. Now, if statements don't just choose between two blocks, they also have some way of lazily evaluating them. So in the case of JavaScript, we don't have lazy evaluation. So what an if statement is we take in some Boolean, which is going to be our condition. We then take in an if function and an else function. If that Boolean is true, we call the if function and return the result of that. If it's false, we return the else function after it's called. So if then else takes in a Boolean, an if block, and else block. It then calls the Boolean function, passing in the if block on one side, the else block on the other. That'll pick one of the two, because the Boolean picks one of them. And then we go ahead and call the result of that. Now remember, we can't have a function that takes in 0 arguments. So that if block and that else block has to take something as an argument, so we'll just give it null. We could give it anything because no one's ever going to end up using it, but null is our useless value, so we'll just pass it in.
That's not the same null that you define.
That's the same null I defined up.
Oh, okay.
So we can just inline that to say x to x. Doesn't matter.
Why don't you call it just identity? Doesn't that make more sense?
It's just traditionally it's called null. The null function and the identity function are the same thing. It's just identity specifically means I am using this as an identity function. Null just means this is the closest thing to an empty value that I have. So in JavaScript, we could effectively just call it without anything. But again, we've created these arbitrary mathematical rules where we always have to call it with one thing. So that's why we pass in null. Everyone good? All right. So now we went from only having functions to now we have Booleans and the basic Boolean operators, and we also have if blocks. Next useful thing to do is to have pairs. We'll eventually work on building lists or maps, dicts, you can build up all that, but a pair is a really, really simple data structure to build. So let's think about it. A pair is a joining of two values. But if we don't do anything with that, then it's not really a function. So what is it that we do with those two values? Well, we pick, do we want to see the left one or the right one? Whenever we pass around a pair, at some point when we pass that around, we're also going to want to call a function that picks to get out the left one or the right one. If we never pick out those values, then it effectively didn't do anything. There was no point in putting them in a pair to begin with. So the way we represent a pair function is it's a function which takes three arguments, a left side and a right side, and this can be anything. This is untyped programming, so we can pass anything in there. We then give a choice function, and we return calling the choice function with left and right. So what will happen is, if we want to create a pair, we'll call the pair function, passing in our left value. Let's say the left side is true, and then we'll pass in the right side, which we'll say is false. And then we won't call the next bit, we'll pass it on to the next person. Then whoever uses it, they can pass in a choose function and tell you, do they want to see the left side or do they want to see the right side of that value? Now to make it easier to do that get left and get right, we can implement them as functions. So given a pair, the get right or get left function takes the pair and just passes in true, because true is a function that returns the first object, which in this case is the left side.
Sorry a second. So pair is a partial applied pair, or up to the left and right, or you also have the choice?
So pair is another way to write this would be
like this.
Like this.
Without choice. So you need to pass the choice, right?
Yeah, so if you need the choice in there, because if you didn't have the choice function, you wouldn't be doing anything.
Exactly, yeah.
So choice goes in, takes it left, then passes back another function to take it right, and something with both.
Right. So it is saying, look, I don't know which of these two things you want. Give me a function that picks them. I'll give them to you, and then you can pass in one that gets the left one or one that gets the right one. So if we want to take a pair and pass it into this get left function, all that it does is it passes in that true function, which if you remember takes in two values and returns the first of them. In this case, the first one that's passed in is left, so it's going to pass the left side. If we want to get the right side, exact same thing, but we pass in false. So now we're picking the second of the two options, which is the right. You could also rename these true and false function, pick the first one and pick the second one. Just in this case, they're the same things, we might as well just use them.
Are those lowercase pairs instances of the uppercase pair?
Yeah, you could think of it that way. The uppercase pair is basically a make pair function. I just wrote a pair to make it a little bit cleaner when we go later on. But yeah, it takes in two values and then it makes a pair function out of it. Everyone following? We good? All right, so numbers. Numbers are where it gets fun. How do we create functions that represent numbers? Now, there are many different ways to do this. There are actually many ways to implement all of these. There are probably infinitely many ways to implement it. But the one that I'm going to show you is the original one that was created with untyped lambda calculus called church encoding. It's one of the simplest ones to understand. In this, you can only create positive integers. 0, you also get that. And if you subtract down past 0 to go to a negative number, it's just going to continue to return 0. So there are positive integers with 0, and it floors at 0. You can get infinitely large, but you can't get any smaller than 0. If you try, it's just going to be another 0. All right. Yep.
Is that a limitation that you have to have that limitation, or it's
That just happens to be the limitation of church encoding. So remember, we can encode anything. We could create signed integers. We could implement floating point. We could implement 64-bit integers. We could implement any kind of number that we want because this is Turing complete. Church numerals just happen to be the one that was created in the 1930s when all this was researched. Though it's based on something called piano numbers, which goes back even further.
For the natural numbers, yeah.
Yeah, they're subtly different. Piano numbers, you can't do that floor thing. Church integers, you just have to get it for free. But in this case, they're just the easiest ones for us to learn. So how can we represent numbers as doing something? Because everything's a function, so the numbers they can't just be a pure value. They have to actually do something. In the case of church numerals, what we're going to represent numbers as is the repetition of some function. So you can think of this as like reduce, except instead of reducing across an array and taking the previous value and then whatever value from the array and passing those into some function and compacting all those together. Instead, we're just going to write a reduce function that doesn't take an array. It just takes in some initial value, and then it calls some function with that initial value. And then it calls the function again, passing in the result of that. And then it calls the function again, passing in the result of that. So what this ends up looking like.
So is that like O(n), the larger your number gets?
Yep.
Okay.
It's fun. I had to write out 64 at one point this way. It's a very large function.
Yeah.
So 0 is a function which takes some function that we're going to repeating, which we'll call func, and it takes some initial value, and it just returns the initial value, because we're going to call that function 0 times using the initial value. In the case of 1, we're going to call that function 1 time, passing in the initial value. So now we have performed that function once, starting with the initial value. 2 is calling that function on the initial value, and then taking the result of that and passing it into a function again. 3 is the same thing.
Couldn't you write 2 in terms of 1?
No, 3 functions.
We could write it in terms of 1 and build it up that way. This just makes it a little more explicit so you can read it.
I was just wondering if there's some type of induction going on.
Yeah, so each one builds off the previous one.
Yeah.
You need 0, and you need either an increment function or 1, and then you can build up the rest of them. So if you're writing a program using this, which you can do, you don't need to define every single integer that you're going to use. You just need to define some core integers and then some math operations, and then you can build every single other number that you need using those. So let's say we want to inspect it.
In your opinion, do you think it's a good reason you don't do it this way?
Yes.
Okay.
Subtraction, the normal way to do subtraction, is super inefficient, as we're going to see.
But addition is constant time. Even multiplication is constant time.
Yeah, both of those are constant time, which is fantastic. Subtraction gets nasty. There are ways to optimize it. We're going to see. Subtraction is the gnarliest thing that we're probably going to look at. All right, so this is all fine and good, but let's actually run some of this code. Now, if we take our 3 function here and log in, JavaScript is very helpfully going to tell us we have a function. In this case, it's assigned to a variable called 3. This isn't very helpful for us because we want to actually know what is that number, because we're going to be performing math with these numbers. So we need some way to take a church numeral and convert it into a JavaScript function. So what we can do is we have this function. So what we'll do is we'll create a function called toNumber. We'll pass into it the church numeral that we want. And that function that we're going to repeating is going to be an increment function. So it'll just take the previous value and add 1, and then we'll start with 0. So if we look at this, if we pass 0 into here, it's just going to return 0. So we'll get 0 out of it. If we pass in this 1 function, it'll take this 0, and then it will call it with this increment function, so it increments it up to 1, and then we'll return that, so we'll get 1 back. 2 will increment it twice, and we'll get 2, et cetera, et cetera, et cetera. So you can think of church numerals as basically taking an increment function and then a 0, and then starting with a 0 and incrementing it up. But it's even more generic than that, because it doesn't have to be an increment function. It's just any function that you want repeated n times given an initial value composed together. So if we call our toNumber here with our 3, we will get back the number 3. Amazing. We have gotten the number 3. We're the best computer science. Numbers aren't very useful unless you can do math with them, so let's start figuring out how to do math with them. Addition is one of the simplest ones to do. If you think about it, this way we're applying a function multiple times. To do addition, we need to apply that function a number of times, and then we will take the result of that, and then apply the function again b number of times. So now we have applied the function a plus b times. And if we look at that, we're going to take, in this case, call x, and we take in y. And what we have to do is here, we have to wrap it in a function, because let's remember, JavaScript has eager evaluation. It's not going to lazily evaluate this. We need to, after we pass in x and y, we need to return another number. And what's a number? It's a thing that takes a function and an initial value. And in this case, the value for that number, what happens when you pass in a function and initial value, is we're going to call x using the function that you gave us. We're going to call that function x times, and the value that we're going to give it is the result of calling y, given that function, the initial number of times. So if we look here, if we just look at this inner bit, here we are just getting whatever y returns, whatever value y happens to return, we call that function that number of times. And then we are taking x here, we're telling it to start with that value instead of 0, and then continue to call that function that many more times. Does that make sense?
Yes, but I have a question.
Yep.
So I remember back in the beginning you were saying that you can't use things that aren't passed into your function, right?
Mm-hmm.
But if we're looking at this, our each of these functions are using something that was defined in the scope outside of it, right?
So if something comes from an outer function, you do get access to that. But what we can't get access to is like 3. We can't just magically have access to 3. We have to, if we use something like that const 3, we have to be able to inline it.
So like your y function is, since it's in our add function, we're allowed to reference x in our y.
Yep, so you'll see everything that we're doing is one expression. Anything outside of that expression we can't get access to. If we do use it, which we will later, we have to be able to inline it. That's the rule. Does that make sense? Okay. All right, so let us see how good we are at math. We will say console.log. We will call the add function with 1 and 1. And this will give us a function, not very interesting. We're going to go ahead and take that function and call to number on it, and we get 2. Yeah. Even more impressively, if we pass in 3 and 3, we get 6. We didn't define 6 anywhere, and now we magically have the number 6 by adding together 3 and 3. Wizardry, as far as I'm concerned. All right. Multiplication is actually not that much more complicated than addition. In the case of addition, we're taking the initial value, we're calling some function that number of times, and then we're taking that result and doing the same thing with another number. In the case of multiplication, instead of having the initial value be the thing that we're passing along, we actually just want to repeat one of the number functions. Because multiplication is just repeated addition. So we can just take one of our number functions. So let's say we are multiplying 2 and 3. What we're going to do is we're going to take that 3 function and we're going to call it 2 times. We're going to pass in that 3 function as the thing that we're repeating. So in this case, multiplication, we're taking x and y. Then we're going to return a number, which remember a number is something that takes in a function and initial value. And then the result is going to be, if we look here, we're calling x and we're passing in the initial value that he gave us. We're starting at the base value. And then we're going to repeat some function. And each time we repeat that function, we'll get the value of the previous repetition. So we're going to have some other function in here, which takes in that value repeating, we're calling it z. And then it calls y, starting at z, and then continues to call the function on it. So now we are multiplying the number together by repeating the function calls. And if we want, we can say console.log to number multiply, let's say 2 and 2. And lo and behold, we get 4. Yep.
Is there any way that you can make the definition definition and multiply, or write the definition and multiply in terms of add, because that's usually how I think of it, as like you were repeating like this addition function X number of times.
You can, it's just a little bit more verbose.
Okay.
So what you could do is, yeah, you could take this in and you just call the add function with it. This basically is the reduced version of that.
Okay.
Any other questions?
That's a need of us that are reduced.
Because they're very similar. All right, an increment function is very simple. We're just simply going to take in a number and call add on it with 1. This will be useful later because we're going to need an increment function. The next question is, how do we do subtraction? Alonzo Church, the professor who came up with all of this, who was a colleague, or at least a compatriot of Turing, he's the Church in the Church-Turing thesis. He came up with this, and at first he tried to create a typed version of it. That ended up having a number of problems with it. So then he created untyped lambda calculus. That was shown to be mathematically sound, and then he later went back and was able to create a typed version. With the first time he did the typed version, he found that there were programs that you could theoretically write, which weren't possible in the typed version, so he had to tighten up his type system. Mind you, he was doing this in the 1930s. Computer science wasn't very advanced back then because there weren't really computers, so type systems took a little bit to get there. When he was coming up with this, though, he came against subtraction. And he thought subtraction may have been his downfall, because he could not figure out how to subtract two numbers. We can add very easily, we can multiply easily, because then we're just increasing the number of function calls. But how do we unwrap a function call? It was actually one of his graduate students who, as the story goes at least, was getting a wisdom tooth removed at the dentist. And while in the dentist chair, he figured out one way to do subtraction, which is now called the wisdom tooth method. So it's great because this thing that the great Alonzo Church couldn't come up with was invented by one of his grad students, thus allowing him to flush out all of untyped lambda calculus. So the key to the wisdom tooth method is subtraction is just repeating some decrement function. That's the first key. So remember, addition, we're repeating some other function. In the case of subtract, we're just going to repeat some decrement function. Decrement is the hard one. Once you can subtract by 1, it's easy to do, but getting the subtract by 1 is hard. So if we look at subtract itself, we take in an x and a y, and what we're going to do is we're going to take x as the initial value, and we're going to call decrement on that y times. So now we're able to get it down. So the question is how we implement decrement. This is where we have to use pairs. So before we look at it, the way this works, and it's going to take a second to get your head around. What we're going to do is we're going to iterate all of the numbers that we'll go through. So we're going to build up a number. We're going to take our input number, x let's call it, and then we are going to start counting. 0, 1, 2, 3, 4, 5, 6. And at the end of calling x, we'll have another number that equals x. So we're basically, by calling that increment operation, we are going to slowly increment some other digit that we start with, in this case, the church numeral for 0. We're going to start with that, and we're going to increment it up. So now we'll have two numbers that are equal to each other. This isn't very helpful because we just created two numbers that are just the same. We already had that number, but we can record that process as it goes along. So we'll start with a pair of two zeros, and then each time that we increment it, we'll increment one of those zeros, and we'll copy the previous value that we got over to the other side of the pair and return a new pair. So now we have a pair where one side is being incremented up by 1, and the other side is always going to be the previous increment value. So what we can effectively do is add up that number all the way and keep track of whatever the last number we did was, and then just go ahead and pull that value out. So we are implementing subtraction via repeated addition, and we're just memoizing a previous value. So intuitive. I'll note this is not the most efficient way to do it. There are more efficient ways to do it, but this was the original method. It's also one of the easiest to understand.
So did the grad student have more than one tooth pulled? Did the grad student have more than one tooth pulled?
I don't know. They probably were working on this for a bit. So if we look at our decrement function, if it'll open, there we go.
Right.
It looks messy, but let's walk through it step by step. We're just going to get the right value of a pair, because remember, we're building up a pair. The left value is going to be the one that we're incrementing. The right value is going to be the previous version of that increment. So at the end of it, we're going to have a pair, and we want to get the previous number, the one that is 1 minus the number that we gave it. All right, so then we're going to call our number x. We're going to call that function, and the initial value that we're going to pass in is that pair of 0 and 0. So now we have our initial value. The function that we're going to repeat, well, let's just look at what would happen if we decremented 0. If we decremented 0, we're going to start with a pair of 0 and 0. We will then call this messy function here 0 times and return this pair, and then we'll get the rightmost value, which is 0, and so we'll return 0. So decrementing 0 just returns 0 again because we are unsigned integers. The function that we're going to repeat takes in the previous value, and it's going to return a new pair, because remember, we're just returning new pairs each time. And the rightmost value is going to be whatever the previous value calculated. And then the leftmost value is simply going to be whatever the previous value calculated plus 1. Does that make sense? So now, in this pair, each time we call the function, this 0 will go up by 1, and this 1 will be whatever the previous value is. So the first time it gets called, this 0 here gets copied over here, which is a no-op, and then this 0 here gets incremented by 1, which gives us 1. The next time, this pair here, this is the 1, remember, that we got from last time, that gets incremented to 2, and then we copy that 1 that we had previously over here, and so this becomes 1. So as we repeat it, we're always keeping track of the previous value, and then this get right pulls out the previous value. Does that make sense?
So
Yep.
this way you're going to decrement by 1 only, right?
Yep. So this gets us a decrement value. This just gets us down 1. And then to subtract, we simply repeat the decrement function.
Gotcha. Yeah.
That is why this is inefficient. Every single step we go up, we have to go through every single digit of the other number. You could memoize that and then simply get that out as a list, but that's a little bit more complicated because we would need singly linked lists to implement that. We'll do that later, but in this case, you can do it without them. So this is the simplest implementation, but not the most efficient. So each time the number gets larger, it gets more and more and more complicated. Question?
Yeah, I was going to say, you're essentially just like brute forcing it, right? You're essentially going from having a number between 0 and x and saying, are you 1 less than x? And then basically just going through the entire list until you actually get to the second to last element.
Yep.
Oh yeah, you are 1 less than x.
Yep.
Okay.
It's nasty. And I have implemented programs that call this a lot. This is usually the bottleneck of your program, is subtraction. Which is great. I've never before had to optimize code by trying to remove as many instances of subtraction as possible. Division, go ahead. Division is just repeated subtraction. So you do a similar thing with a pair, you just subtract the number that many times, and you keep track of how many times you can subtract it before it hits 0. So you subtract it, you check whether or not you're equal to 0. If you are equal to 0, then you've managed to hit the number that you want. If you're not equal to 0, you subtract again. Is that equal to 0? Each time you repeat that.
So you're implementing it and then you're storing that in the right side of there.
Yep.
What if you have two numbers? What if it's not divisible though? I mean,
This is integer division, so you actually end up for free getting modulus because you're keeping track of the remainder. It's computer science modulus, not mathematics modulus, that you can also implement that. So you're basically doing integer division where it's always going to be rounded, but you also have access to the remainder value. So it's like when you did division back in grade school. Yep.
You were mentioning that this was, like, subtract was the sticking point for church, that without this, without subtract, it's not Turing complete? Like,
Well, 'cause
why was this a sticking point for him?
This was just hard to figure out how to do.
No, but even if he hadn't figured it out, like, is the language the university is working in, like, less?
So subtraction is a computable function. And to be Turing complete, you have to do all computable functions. I also know it's really funny to call this Turing complete. This was created before the Church-Turing thesis, before the whole Turing complete thing. So also Gödel did his recursion stuff, which let's not even get into that. But this was Turing complete before Turing complete was even a thing, man. It's like hipster Turing complete. But if you want to be able to compute everything that's computable, subtraction is one of those computations. So like he could have if he has a mathematical proof that this can do anything that's computable, then it has to be able to do subtraction. So this is just one way to do it. There are infinitely many ways to do it. This is just one. All right, so comparison with numbers. We have two numbers. It's good to be able to compare them and get back a Boolean value. To implement these, we first need some function to check, is a number 0? This, luckily, is very easy to do, because let's remember, 0 is just a function that takes some function that we're going to iterate on and some initial value, and it returns the initial value. So how do we check if a number is 0? We take a number, and we pass into it an initial value of true. So 0 will just return the initial value, true, because 0 is 0. Then for the second one, we're going to pass in a function where we don't care about the argument that gets passed into it, and we're just going to return false. Because if this function ever gets called, you are not 0, therefore false gets returned. So now the function will check whether or not a number is 0. Yep.
So does that not work if you call 1 with null?
What do you mean? So if you call
1 with the function null.
If you call 1 with the function null, yeah, but here we're not passing in null. So if you pass 1 with the function null, it will effectively be 0 because you're repeating an identity function n times, but it is repeating the identity function. It's just that the identity function is effectively doing nothing. Good question. So the next easiest comparison to implement is actually is greater than or equal to. Greater than and less than are actually harder to implement. So what's one way that we can implement is greater than or equal to? We take in two numbers, we subtract them from each other, and we just check if that's 0. Because if one number is greater than the other one, if we subtract that bigger number from the other number, it's going to floor at 0. And if it floors, we know that they were equal to each other or it was bigger than it, and therefore we can check it. So now, from that, we can get if two numbers are equal. And the way that we do that is we check if x is greater than y, x is greater than or equal to y, and y is greater than or equal to x, then do it. Note that this is performing subtraction twice for both sets of numbers, which is calling the decrement function a heck of a lot as numbers get larger, like a whole heck of a lot. Which means equal is actually a pretty expensive operation with this particular implementation. Let's say you were to implement binary numbers, which you could do by just having a list of Booleans. Their equality would be much cheaper. You would just look at each individual value, check if all of them are the same, and then you would be good. However, if you want to do addition or subtraction with binary numbers, you put together all your logic operators to build half adders and full adders, but that ends up being very computationally expensive, which I can tell you from experience. It is slower to do that. So addition is better with binary, or equality is better with binary numbers, but all your other mathematical operators end up being more expensive. It's also really hard to read logic circuits that are written out as functional programs. It's not a good way to design circuitry. Does anyone have any questions? So if you'd like, we can go on. The only other thing I have is lists, which aren't actually as bad as a lot of things we've seen. There's a little bit more code to them, but they're actually very simple to do. So if you want, we can go ahead and look at that. Do you want to look at that?
I would like to know more of the history after the list.
Okay. Alrighty. So a list in this case is going to be a singly linked list. So it's going to be made up of a series of nodes, or if you're a Lisper, a series of con cells pointed to each other. If you're not a Lisper, I just said a logic version, and I'm sorry. So a list node is going to be a collection of three things. It is going to be the value at that node, whether or not this is the end of the list, and then the next value in the list. So we're going to have the value for that point in the list, whether or not this is the end, and then the next value. So list node here is a constructor function to create a list node. Remember that everything has to be, a function. We can't just store data and later do stuff with it. So just like we did with Booleans, just like we did with numbers or pairs, we're going to have some choice function to pick which one of those three things do you want. So a list node takes in whether or not you're the end, a Boolean value for that. It takes in the element for this particular node, and then a pointer to the rest of the list, which is just a pointer to the next node. And then you give it some choice function later on. It then calls that choice function with those three things. So this is similar to what we have with a pair, except this is a tuple with three components. The empty list is simply creating a list node where the isEnd variable is set to true, and then the rest are just nulls. Because we're at the end of the list, there are no values stored at the end of the list. Just for simplicity, if you're at the end of the list, there are no values. After that, there's nothing, and at the end of the list, there is actually nothing there also. This makes it a little easier.
It's like the sentinel value.
Yep. All right, so if we can create an empty list, which has nothing in it. How do we build this? Well, we can start appending onto it. In this case, I called it unshift, which people maybe used to shift gets the first item off of the list. Unshift puts it on. This is basically like push, except it does it on the other end. Push is actually harder to implement because we have to go through the list. We'll see that. Yeah?
Sorry, are you appending, prepending?
Appending. All right, prepending. This is prepending.
Okay, so it's a cons, basically.
Cons is the other way to call it. I was tempted to call them all by list terms, but I mean, most of you aren't list programmers, so like we're not going to do that. But yeah, if you're familiar with list, this is your cons function. So what do we do?
Sorry, shift is for hipster, right? It's a hipster, right?
Yeah.
Shift.
No, this is more C programming.
Okay.
If I called it append, it would be more like generic scripting language. If I called it cons, then I'd be old and bearded.
Yeah.
What's the hipster term?
Oh, I don't know what hipsters would call this. Dank. All right, so unshift is a function that takes in some list. It takes the element that we want to append onto that list, and it creates a new list node. It's not the end of the list. Then it stores the element, and then the next item is whatever the list you gave us. So if we want to create a list with one element, we pass in the empty list, and then whatever element we want to go in there, and now we have a list of one item. Everyone good? If we want to check, are we at the end of the list? If we have a list, is this an end of list node? All we do is we take the list, and we pass in a function that takes in that isEnd value. It also takes in the element value and the, what's the other value?
Rest of the list.
The rest of the list, yeah. Because we have to take those in, and then it just returns the isEnd. I did those underscores because we don't use them. So all that we do if we want to check at the end of the list is we just pass in the list, pull out that isEnd value, and then just return. Filippo, you're looking confused.
Yeah, I was trying to.
In this case, like it doesn't complain that these two variables have the same name, or these two parameters have the same name, that one is just overwriting the other one in this case. I did the underscores just so that you don't get confused because we're not using it. So what happens if we want to get the first element of the list, or the car if you're a lisper? We're going to take in a list, and we're not going to deal with that isEnd value. We're going to take the element that is the element that that list node stores, and we're going to take the rest. We don't care about that, and we'll just return the element because that is the first element of the list. How do we get the rest of a list? So how do we get the cooter if you're a lisper? Same thing, except we go to the last. However, let's say we have an empty list. If we have the empty list, the last element is null. We don't want to return that. We always want to return a list so that you're guaranteed. If you call rest on an empty list, you will get another empty list. So we say, if this is the end of the list, call a function that returns the empty list. So if we're at the end of the list, just return empty list. So if you pass in the empty list this, we have our base case. If it's not the end of the list, we're then going to pull out that else. And so that gives us good safety. We could omit this if-else stuff, the empty list, if we always know the length of the list. But because we're going to be recursing over this, we don't necessarily know the length of it. If you want to like store a tuple, you could then store a number with it and then know how deep you can go safely. But in this case, we want to implement it more generically, where we don't know how deep this list is, so we can just always get the rest of it. How do we get the nth item of a list? So this is indexing into a list to get a certain item. We're going to take the list, and we're going to take that value n, how deep we want to go in the list, and we're going to get the first element of taking that function n, and we're going to start with the list. So let's say the function gave us a 0. It's going to then call this function 0 times, so it effectively isn't there. And it's just going to return the list. And then this first here will get the first item of the list. And so the 0th element is the first element of the list you gave us. Simple. If we pass in 1, it'll call this function 1 times, where it takes the previous list. In the case of 1, that's the list that you gave it. And it gets the rest of it, and then gets the first one. So if we pass in 1, it'll go 1 step into the list, and then return that element at that node. If we pass in 2, it'll go in 1, and it'll take that list, that new list, and go in 1 more element, and then it'll give us the second element in the list. And so we have zero indexing into the list. Does that make sense? So how do we get the last element of the list? It is a little bit more confusing. Let's write it this way first. I'm going to go ahead and delete this weird stuff, which we'll get into in a moment. The easiest way to think about this is we're going to take some list, and if the next element in the list is the end of the list, because remember the end of the list doesn't store any values. If the next element is the end of the list, we're going to go ahead and give you whatever element is stored here. So if you have a list with 1 value, the next element is going to be there, and so if you have an empty list, the rest of the list is also going to be an empty list, which is also the end of the list. And then we're going to get the first element out of that, which in this case is null. If you try and get the last element of an empty list, you get null back. That's pretty good. So how do we get the other elements? So let's say the next element in the list is not the last element. What we're going to do is we're going to recursively call this last function using the rest of the list. So we're going to keep recursively going through this function to try and get until we just before the last element, and then we'll pop that out, and that's the last value. Does that make sense? So in this, I have violated the rule that I told you before. I cannot go through and replace this. The if then else, I can go in and copy the implementation of that and paste that in there. The is end, I can copy that and paste it in here. Rest, I can do the same first, but here I'm using the last function. So here's my implementation of the last function. As I told you before, anytime I'm calling one of these constants that I find elsewhere, I should be able to inline it. So I should be able to copy the implementation of last, which is this, and then paste it in there. But oh wait, I've called last in here. Okay, but I can go ahead, I can just take my implementation of last, which is this, and replace it with the implementation. But there's last again. This will go on infinitely.
You should have a length count.
Yeah, so yeah, sure. We don't want to have a maximum call stack size because that would not be Turing complete. We wouldn't be able to compute anything because if we want to be able to compute anything, we need to be able to compute lists that are almost infinitely long. They need to be able to be as long as possible, and we can still get the last item out. And if we had if we just kept pasting it in, at some point we would stop, and if the list was 1 longer than that, we wouldn't be able to get it. This was another big problem for untyped lambda calculus, because it was known that there are some computable things that have to use recursion. You can often remove recursion, but there are certain things where you have to be able to do recursion in order to compute them. Or you need to have something that can simulate recursion. So, in untyped lambda calculus, there ought to be some way to simulate recursion. But how do you simulate recursion if you don't have recursion and you don't have assignment? The way you do that is with the Y combinator. It's a mathematical function which takes in a higher order function, or it's a higher order function. It takes in a function and then turns it into a recursive function. Now, JavaScript, again, is it's an eagerly evaluated language. So you cannot have laziness in it, which means we can't use the actual Y combinator. We have to use what's called, I believe, the applicative order Y combinator, also known as the Z combinator. So I've defined the Z combinator up above. It's some function, and what it does is, it allows us to pass in a function, which here we have this thing recursive last. That value, the Z combinator passes into there something that acts as if we're doing recursion. So here we replace the instance of last with that, and now you notice this last function, it doesn't actually reference itself. It has a value which we're told is like you're referencing yourself. This recursive last operates exactly the same as this last, but we didn't get it by actually referencing last. Instead, we got it by taking our function and passing it into the Z combinator. Does that make sense?
Where's Z defined?
I will show you Z. So if you want, another time, we can like, at a different talk, we can go through how Z works. I have a friend who spent like a month or two by hand going through the Z combinator to figure out how it works. The version I'm going to show you is not the most compact version, though it is very compact, but mathematicians like it because it's symmetrical. It's a very pretty version of the Z combinator. It looks like this. So we take in our function, and then we do stuff to it, and it returns a recursive version of that function. I could give these names. It would not help you in any way. You kind of have to build it up from scratch, and then, as my friend did, spend a month kind of staring deep into the beast, and eventually you get a revelation. Or you go insane. I don't know which. However, now that we have the Z combinator, that is a generic recursion function. So now we can just use recursion everywhere without actually using recursion. Push, how we get the append versus prepend, is going to recursively call the push function, and push takes in the list that we want to push onto, the element that we want to push onto, and then it asks, okay, is this the end of the list? Is this that empty list that we had before? Pushing onto an empty list is the equivalent of unshifting onto it. Prepending onto an empty list is the same as appending onto an empty list. So we can just do unshift, works the same way. What happens if we want to have a list that's longer than 0? Well, we're going to go ahead and we're going to unshift onto the first element of the list the result of recursively pushing that element on the rest of the list. So it's going to recursively go through the list until it finds that last element, put that on, and then unshift the rest of the list back onto it. Not super efficient, but it works. Map and reduce, which are like everyone's favorite functional programming things when they're first learning them. Those are implemented similarly. We're recursively going to take in the case of reduce, the list, the initial value, and then the function that you want to go ahead and reduce on. If it's the end of the list, we just return the initial value. That's super easy, because empty lists are really easy to deal with. If it's not an empty list, we're going to recursively reduce it, where the list that we're going to recurse on is everything except for the first element, because when you recurse, you generally want to make something smaller so that you don't get stuck in an infinite loop. Now it's guaranteed to terminate. The initial value is going to be the result of calling the function with the initial value and the first element of the list. So now, the first time we call it, we're going to take the first element of the list, we're going to take the initial value, then we're going to put them together, and then we recurse the function. So now, each time we go through, the initial value is being changed to whatever the previous call to the recurse function was. If you're not like picking up on this, I can share this code with you. It's a little hairy, but I mean, it's basically you're just recursing over it. And each time you're making the list a little bit smaller until eventually you get to the end. Yeah?
I know we don't have much time, but I have a very good question. Why you call that reduce instead of fold right?
Yeah, so this is reduce right or fold right or fold depending on what language you're in. most people here, if they're used to this function, are probably used to one called reduce.
Reduce, okay.
Because if you're in JavaScript or C or Python or kind of Ruby, it's called reduce. If you're in Haskell, Scala, etc., it's called fold. Right. Yeah. And this is fold right. You can also do it where it does it the other direction. Map is very similar. We're going to recursively reduce. We're implementing map as reduce. And we're going to start with an empty list. And then each time what we're going to do is we're going to push the previous element onto the result of Colin function. So we're going to take the previous list and then we're going to just push on the next element. So we start with an empty list and then we build it up with each of the values from reduce. And that's the equivalent of calling that function on each element of the list. That's all. No, this goes at focus. This goes 0, 1, 2, 3, 4, 5.
Yeah, inverse of reduce.
No, this goes in the same direction as the reduce. So the reduce is going from 0 to the end of the list. This is going from 0 to the end of the list. If you want to see like how complicated this can get, I have done one very heavyweight program using untyped lambda calculus. This is written in Ruby, so the syntax is a little different. We'll go ahead and zoom in here. I'm going to go ahead and cat this program. Yeah, so people who work with me have seen this. It's a very simple program.
Whoa.
So what we have here is we have one anonymous function, which starts here, and it has a number of nested anonymous functions. I ran out of all of the letters of the alphabet because everything needs to be a single letter variable name for this program to work. So it also has the Greek alphabet, most of the Russian alphabet, some other symbols.
And the remainder of the Unicode character set?
And then we get to the end here. So this is all one function. Then there's a little bit of Ruby code, which just translates those values into something usable. If we zoom out, the program is a lambda chess. If we call this program, so we're going to go ahead and pass into the Ruby interpreter this program. When we zoom out, the program rewrites itself. The rewriting is done in Ruby. It's not done in lambda calculus because I'm not that crazy. So it rewrites the program to look like a chessboard. So now that lambda calculus, all those lambda functions are now in the shape of a chessboard with SDR chess pieces. Now what all this function does that's in the chessboard is it is all the rules of chess and a chess AI that isn't very intelligent that you can play against implemented untyped lambda calculus. So if we go ahead and call this, we can take the lambda chess. We want to do a move, so let's say we're going to take B1 and we're going to go to C3, so we're going to move the knight on the left-hand side. So if we zoom in, we can go ahead and take B2 and move it to C3. The interpretation of the move in terms of like where the coordinates you want to move to, that's done in Ruby, and then that gets passed along with the board state into the lambda calculus. It then calculates out, is that a valid move, given all the rules of chess and even as the obscure ones. If it is valid, it moves the piece, then takes that, passes into a chess AI, also implemented in the lambda calculus, then calculates a valid response move if there is one. If there isn't one, you beat it and announces that, and then gives you that new board state. So if we go and take this, and in this case, I'm going to pass it into the key function so we can keep track of it. Then we'll run it, and I believe I made a mistake because if we zoom out, it hasn't moved the piece, but it says that it's invalid. So let's go ahead and see what I did wrong. Hold on.
B1.
B1.
You might agree to.
No, because it's at, oh yeah, B1. Yep, you're right. It's like a giant pair of program essentially.
Yeah.
So we're going to move B1 to B3. It's a little slow because I want to see if I can speed it up, but okay, so it has finished its computation. It returns a new program, but it re-renders the white space, moving that knight, and then it decided to move its knight.
And that's actual the source code.
this is the source code of the next move. So if you take the output to standard out and run that, passing in a next move, it will then return a new program, which gives you the result of you doing that move and the response. If you capture a piece, it takes a little ASCII art for that piece and renders it in this space down here in between the board, and it'll build up sort of like here are all the captured pieces over time. Yep.
Is the code for the AI written in there too?
Yep.
So if I was really, really, really mad at myself, I could sit down and count and figure out every move before it does it.
No, because it actually, so if we run the same program again,
This is randomness, pseudo.
so we can't implement pure randomness in untyped lambda calculus because it's purely deterministic. Everything that goes in comes out. This is true of computers too. Computers take input from the external world, like mouse clicks and network events, to generate a seed number, and then it deterministically generates a random number off that. So one of the parameters that we pass into it is a seed value, and then it has a very, very primitive and not very good pseudo-random number generator that takes that seed value and uses it to randomize it. So if we give it the same move again, it's going to go ahead and think for a moment.
You consider doing Go?
Yes, the pieces weren't as pretty, which is why I didn't do Go. So now return the result. We move the same up. This time we decide to move the pawn. Mind you, if you want to beat it, as far as I know, no one's ever played a full game of chess against this. I need to do a performance optimization, but this wasn't automatically written. I, by hand, formatted the code to be the nice thing, and also formatted so that all of this white space was valid. It doesn't strip the white space before evaluating. All the white space that gets inserted to render the pieces, that's all valid white space as far as Ruby is concerned. It's not put in any bad places. That's all done by hand because it was like a week before I had to go to a conference, so I just did the lazy way, which means for me to patch this and fix it, I have to, the lazy way. I have to actually go into here, figure out where the functions I want to change are, edit them, and then add extra parentheses to pad it out so that the white space can go in the right places, and then rerun it. There is a test suite that will partially test it, so that helps out with this, because you want to write tests if you're doing something like this. But here's an example of like practical untyped lambda calculus. So it is Turing complete, I promise. Anyone have any questions or curious about anything else about untyped lambda calculus? So I'll say again that even though this is like very arbitrary, we're taking like the stupidest, most simplest way to run a program, though there are actually things simpler than untyped lambda calculus, depending on how you define simpler. Even though we're taking this really simple thing and building all of computing from, even though it's very inefficient, this kind of thing is actually kind of how the core of Haskell works. It uses sort of an extended version of this, and I believe early implementations of Haskell did its integers using church numerals like we did. They just, because they're compiling it, they're able to run it a bit faster than Ruby, which is creating a new object each time. I heard Simon Peyton-Jones say that at talk. I don't actually know if it's true, because I haven't gone into the core of Haskell. But if no one has any other questions, then.
Just curious, how many thousand more definitions you need before you could get a IEEE floating point number represented?
That probably would be simpler than the chess one.
Really?
So you could do IEEE floating point by implementing binary numbers, and a binary number is just a list of Booleans, and then you can pipe that together. What you could actually do, if you were special, let's say, is you could take a circuit that does all the operations on IEEE floating point.
Yeah.
You could then take the actual logic diagram for that, compile that into untyped lambda calculus, and then run that.
Yeah.
It probably wouldn't be as efficient if you figured out your own implementation, but you could feasibly do it.
Okay.
I and a friend, because we've done a number of things in this, because we're weird and have weird hobbies, we have implemented object orientation in this. You can also kind of implement mutation, as long as you consider mutation as you have some global state that's being passed around, which each individual global state isn't being mutated, but you're giving a new one each time, and so it's kind of like mutation. So like theoretically, you could implement the C compiler in this, and then you could take C code which has mutation in it, and run it in this. But I mean, that's an exercise for homework. You had a question?
Yeah, everything we've covered here tonight, this is enough for Turing completeness, right?
So you can't show that something is Turing complete through this kind of method, because theoretically there could be some other function that you can't do with it. What you need to do if you wanted to, by implementation, show Turing completeness, is implement something else that is Turing complete. So like, let's say we know that brainfuck is a programming language that's Turing complete. If you implement a brainfuck compiler in untyped lambda calculus, because brainfuck has been proven to be Turing complete, and you can run brainfuck in this is proven to be Turing complete. The way Alonzo Church did it was by writing math. He didn't just write out a bunch of programs, because there wasn't a concept of Turing completeness. The reason why all this was done was he was doing research into the foundations of mathematics. So one question in mathematics is, what is computable and what's able to do that? So this was to help answer some questions about what is computable and what's the definition of computation. Not in terms of computers running something, but in terms of functions that can be done in a certain way. There are certain functions that are knowable but are not computable, but that's a subject for another day. So there are things that this can't do that a mathematician knows to be true, but those are things that a computer also can't solve without additional details. Kind of. It gets weird. Any other questions? All right, thank you.